How do geotechnical engineers measure soil shear strength? Imagine trying to determine how much soil can withstand before it begins to slide or collapse. This is a fundamental aspect of geotechnical engineering that ensures the safety and stability of structures such as buildings, bridges, and dams. To understand how engineers accomplish this, we need to explore the methods they use to quantify soil shear strength. One of the most common laboratory tests is the direct shear test. In this procedure, a soil sample is placed in a shear box divided into two halves. The sample is subjected to a normal load that simulates the pressure exerted by overlying materials. Then, a shear force is gradually applied along a predetermined plane within the sample. The test records the maximum shear stress the soil can sustain before failure occurs. This maximum value indicates the soil's shear strength under the specific conditions of the test. The results are often used to derive parameters such as cohesion and internal friction angle, which describe how soil particles interact and resist sliding. Another widely used laboratory method is the triaxial shear test. In this test, a cylindrical soil specimen is enclosed in a rubber membrane and subjected to controlled axial and confining pressures. The confining pressure simulates the stress from surrounding soil or structures. The axial load is increased until the soil specimen fails, and the test records the shear stress at failure. The triaxial test allows engineers to evaluate soil behavior under different stress conditions, providing a comprehensive understanding of shear strength for various scenarios. In addition to laboratory tests, field testing plays a crucial role. The cone penetration test involves pushing a cone-shaped probe into the ground at a constant rate. The resistance encountered by the cone provides real-time data about the soil's resistance to penetration, which correlates with shear strength. Similarly, the vane shear test involves inserting a four-bladed vane into the soil and rotating it to measure the torque required to cause failure. This method is particularly useful for soft, cohesive soils. By combining laboratory and field testing data, geotechnical engineers develop a detailed profile of soil shear strength. This information guides the design of foundations, retaining walls, and other structures, ensuring they can withstand the forces they will encounter. Through meticulous testing and analysis, engineers can predict how soils will behave under stress, ultimately safeguarding infrastructure and lives.